Hello everyone, this is section 11.3 in integral tests and the estimation of sums. Now, in general, it's going to be very difficult to find the exact sum of a series that we have, and we were able to achieve that before with the geometric series or the telescopic series, because in those cases we can actually find out what the nth term of the partial sum is. But it's not going to be easy to discover such a formula in general for most of the series, so I'm not going to be able to do that very often. But one good approximation would be to analyze what happens with the partial sum and see if the partial sum is getting to somewhere, and then if it's possible to approximate with another method. So as an example, consider a couple of series. Consider the series of 1 over n squared or the series of 1 over square root of I. So in here, you can see in this table that I'm actually given certain number of terms. So for example, I give 5 terms, 10 terms, 50 terms, 100 terms, 500, 1,000, and 5,000. And then I'm calculating what is the value of the partial sum for those terms. As you can notice, if I have 1 over I squared, I find out that the sum is actually approaching the number 1.6447. So from the point of view of limits, this is saying, well, the limit when n goes to infinity is kind of going to go to 1.64 or to 1.6. You can kind of claim that in there. On the other hand, if I consider the series 1 over square root of I, notice that this is growing and bounded. It goes 3.23, 5, 12, 18, 43, 61, 139. And if you continue giving values, then you're likely going to realize that this is growing and bounded, and this limit of the partial sum is going to go to infinity, and the series is going to be divergent. So I have an example here of convergent and a divergent partial sums. Now, if we consider those series from the point of view of areas, we can kind of see this approximation by rectangles, similar to what we do on the Riemann sums. And so if we use Riemann sums, it's kind of immediate to think of this as, well, if I'm using Riemann sums and I want to go to infinity with the sum, am I not approaching an integral? And that is precisely what's going to happen here. So essentially, I'm going to approximate 1 over n squared with the integral of 1 over x squared, and I'm going to approximate 1 over square root of n with 1 over square root of x respectively. Okay, and so that idea is the principle of the integral test. So now to define the integral test, we're going to suppose that my sequence is going to be given by a function that is continuous, positive, decreasing function in the interval 1 to infinity. And of course that we can see our sequence as an being equals f of n. So in this case, f will be 1 over x squared, and the sequence is 1 over n squared. Here the function is 1 over square root of x, and the sequence is 1 over square root of n. Now, what happens is that if the series is going to be convergent if and only if the integral, the improper integral from 1 to infinity of f of x dx is going to be convergent. In other words, if the integral is convergent, then the series is convergent, and if the series is divergent, then if the integral is divergent, then the series is divergent as well. So let's see some examples of that. Now, the first and most important things that you gotta do when you're doing integral tests is you gotta kind of check for the properties. So for example, we have f of n here in number 1 is 1 over n squared. So continuous, this is clearly continuous. Positive, this is clearly positive. It doesn't have negative values that it can take. Below is a square, and square plus positive, positive. Above is positive. The only thing that I might want to require an F for doing is that is decreasing. But to do decreasing, I can calculate what F prime is. And of course, notice that this is n squared plus 1 to the minus 1. So I can kind of do a chain rule here. This is minus 1 n squared plus 1 to the minus 2. And by the chain rule, which is 2n. So at the end, this is minus 2n over n squared plus 1. And because n is bigger than 1, right? Then f prime here is going to be negative. So we're using criteria of the first derivative for this. And so f prime being negative implies that f is decreasing. And so these are the things that I gotta take care before using integral test. So now that I have all the hypotheses being true, then I can say by integral test, and so I can kind of bound this series on the top here by the integral. And so this is going to be the integral of 1 over x squared plus 1. Now this is an improper integral, so this is equals to the limit when t goes to infinity of 1 to t of x squared plus 1 dx. Now if you remember, this is the antiderivative of arctangent, so this is arctangent of x between 1 and t. And this is limit when t goes to infinity of this. And so pretty much a plug on t and 1. This is arctangent of t minus arctangent of 1, which is going to be pi over 4. And then limit when t goes to infinity of arctangent is pi half. And pi half minus pi over 4 is pi over 4. So this is a finite number, and so we can say that this integral is convergent. And because the integral is convergent, then the series is. The integral is converges, so that implies that the series 1 over n squared plus 1 and equals 1 to infinity converges as well. And that is the principle of the integral test. Now let's do a couple more of exercises here. So exercise number 2 is going to be 1 to the np. And so of course f of n then is going to be 1 over np, which we can clearly see that is positive, and we can see that it's continuous. So these two ideas I get up very quick out of the way. Now f prime of n is going to be minus p times 1 over n to p minus 1. Since we're taking the derivative of this. Wait a minute. Let me write this properly. So the way that I can check very quick the derivative is I write this as n to the minus p. And so that implies that the derivative is minus p n to the minus p minus 1. And so I can rewrite this as minus p over n to the p plus 1. It's the best way to write this one out. So as you can see, this is negative. And so that implies that f is going to be decreasing. And so now integral test is telling me, well, I'm going to take the integral from 1 to infinity of 1 over x to the p. and see was that it. And so let's go a little bit into detail. I'm not assuming that P is anything yet in terms of numbers, but I'm gonna write this as limit when n goes to infinity of sorry, let me use t of 1 to t of 1 over x to the p dx. And so this works in almost a similar way to the derivative. Notice that this is x to the minus p, so this is x to the minus p plus 1 over minus p plus 1. And then in 1 and t. And so when I plug this in t, I'm gonna get limit when t goes to infinity of t to the minus p plus 1 over minus p plus 1. And then when I plug in 1, this is just gonna simply be minus 1 over minus p plus 1. Well, when we get this here, first and anything, we're gonna have a bunch of things that we need to be careful. So let's just open up the cases that this is going to provide. So if p is larger than 1, if p is larger than 1, then this is a negative value, and this is clearly going to go to 0. So this will give me 1 over 1 minus p. This will be if p is bigger than 1. This goes to 0. Okay. P equals 1 is not going to be something that we can really take. P equals to 1 is going to give me log of x, right? And log of x when t goes to infinity goes to infinity. So if p equals 1, that limit goes to infinity. And so now we're going to check what happens if p is between, let's say, less than 1 initially. Notice that if p is less than 1, then this is going to be a positive power here. And so if this is a positive power, then this is just going to be something that is going to infinity. So I could simplify this by saying, well, this is 1 minus p if p is bigger than 1, and infinity if p less than 1, less or equal. Okay. But the difference y in 1 is infinity is different versus y is infinity with p less than 1. With p less than 1, let's say with p being 0, this will be t, right? And so when t goes to infinity, this goes to infinity. This goes to infinity clearly by itself. When p is equals 1 here from the start, we have a log integral, and that's what's going to provide me with a divergent integral. So it kind of depends. So if p is bigger than 1, it converges, and if p is less than 1, then diverges. And so that's one of the things that you can use, let's say, for the following integrals. So if we have the integral from 1 to n cubed, now at this point you know that p is equals 3 is bigger than 1, so it converges. Of course, I'm just doing it here because it's an example. If you ever had 1 over n cubed, you had to do this whole process to actually show me that you know how to apply integral tests. I'm just showcasing here in these two examples that that's gonna happen with this. Here p is less than 1, so it diverges. So I'm just showing you the general case and some applications, but let's say that you have to do 1 over n to the 4. You actually have to show me all the steps with the integral criteria to just showcase that you know how that works. Okay? Don't just tell me P is bigger than 1 converges, P is less than 1 diverges, because I'm going to take out points of U by not showing all the work. This here, since I already show you all the work in the cases, then I'm concluding with the 2 next scenarios. Now, last but not least, I'm going to go with the series of log of n over n. And this kind of looks like something that I can approach by integral terms. Let's see. Clearly this is positive and continuous, so no issues in there. And if I do f prime, then that's going to be, let's see, derivative of log of n is 1 over n times n minus log of n over n squared. So essentially this is just going to be 1 minus log of n squared. So notice that if n is bigger than 1, this is going to be bigger than 0. And so mostly this is going to be a negative value, especially if we go with a number that is bigger than 3. So let's say for n bigger than 3, this number here is negative. So I can go and say, well, yeah, it's going to be decreasing, or in general it's decreasing for the most part. So I can use integral test. F decreases here. So now the integral from 1 to infinity of log of x over x, that looks like a very complicated integral, but in reality it has a very simple setup. So notice that this is equals to the limit when t goes to infinity of 1 to t of log of x, and I'm going to write it here, 1 over x dx. So now that I wrote that in that way, you can probably realize, oh, this is a basic substitution. U equals log of x, du is this one. So essentially that's what's going to happen. I'm going to do a substitution in there. And so I'm going to skip the step of just doing the substitution. U equals ln of x, du is going to be 1 over x dx. And so you know that this becomes u, and this is going to be u squared over 2. So now I'm just going to write it as log of t squared over 2. And why am I writing directly on t? Well, because realize that when I plug log of t in 1 is 0, so I don't need to write that part as well. So this is just log of t power to the 2 divided by 2, but when t goes to infinity, this is going to go to infinity as well. So what happens here is that this is a divergent series. It's a divergent integral, and because it's a divergent integral, then it's a divergent series. So this implies that the series of ln of n diverges as well. Okay, so that's the use of the integral test for one side on convergency and the other side on divergency. Now let's go back to the problem of just doing this for the sake of estimating the sums. So if we're estimating the sums, remember that we are using the integral test, and so the integral test is approximating a lot of this by Riemann sum. So we can kind of take the Riemann sum at the endpoint and use it to estimate what the partial sum is going to be. So in this scenario, I can also find out how much the error is going to be for a particular sum. So for example, if I'm taking the sum of the first n terms, then the remainder of the rest of the terms is just going to be bounded by the integral from n to infinity, right? And also I can analyze, that's if I'm doing it by the right side, but if I'm doing it by the left side, then I can just go from the n plus 1 term, and that's going to help me approximate both left side and right side of the remainder. Now, then the remainder estimate for the integral test will be bounded between the n plus 1 term and the n term for the integral test. Okay, so the theorem here will be, if you have a function that you can see at the sequence where the function is continuous, decreasing, and we have this series being convergent, where Rn is just the difference between the limit where it converges and the n partial sum, then I can see that that remainder is going to be bounded by the n plus 1 to infinity integral of the function f, and the n to infinity function integral to of the function f. So that might look a little bit confusing. So instead of that, let me just actually showcase what will be the approximation using the first 10 terms, and see how the remainder will work out here and how many terms will be required to ensure that the sum is accurate within 0.05 amount. Okay, so let's go here to the board, and so we're going with 1 over n cubed, which we know is convergent, right, by integral test. So what we're going to do is, well, let's write it out, 1 over n cubed, and so let's check the conditions first. F of 1 over n cubed, this is positive, is continuous, and f prime of n is minus 3 over n to the 4, which is going to be negative most of the time or all the time, so that implies that f is decreasing, and so I can use integral tests. And now that I can use integral tests, then let's approximate the sum by using the first 10 terms. And so to approximate that, I'll say n equals 1 to infinity of 1 over n cubed is approximately s of 10, which is going to be what? 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 to the 3 plus 1 over 10 cubed. You can actually do this by calculator. You don't need to do anything specific. And this is just going to be 1.1975. And then according to this, this will be my estimation S, and now Rn, which is the sum minus the n number, is going to be equivalent to what? Or is going to be less than, because we want an estimation, 10 to infinity of 1 over x cubed. This using the integral test. And so if you remember the integral of 1 over x cubed, this is just x to the minus 3, is going to be x to the minus 2 over minus 2, right? So this will be minus 1/2 1 over x squared between 10 and infinity. Since we're thinking about limits, right? So let's call it t here, and now let's make t goes to infinity. Let me actually write the whole thing. Limit when t goes to infinity of minus 1 over 2t to the 4, and also plus, and then the same thing, but now plug in 10, so 10 to the 4. So this part is going to go to 0, and this little piece that is left here is 1 over 200. So the size of the error here is going to be at most 0.05. Okay, so that's not a lot of error, but if we want to just make sure that it's even lesser than that, this is just A. Now for part B, we want that to be 1 0 more, so we want an accuracy of 0.005, and so because the Rn is less than n to infinity of 1 over x cubed, you gotta remember that this is 1 over 2n squared. So using the same thing here, using the same integration method here, and so we're essentially saying, well, we want that to be less than 0.005. So that means that n squared gotta be bigger than 1 over 0.001 or 1,000. So this is telling me, well, n gotta be bigger than the square root of 1,000, which is gonna be like 31.6. So we need 32 terms at least to make sure that we have that level of accuracy. Okay, so notice that we need an n larger than 31. That gives me 32, so that means that n gotta be larger than 32, and 32, 33, n equals 33, 34. It's gonna work out to give me this small of an error. Okay, so that's everything that we can do with the integral test. We can check if a series is going to be convergent or divergent, and we can also check an approximation of the integration of the sum of the series with a calculation of how much the error can be. So it's pretty accurate, and as long as you have that the function is continuous, positive, and decreasing, this is a good method to approximate the partial sum of a given convergent series.